Sorry, you guys. It's just like technical presentation stuff before an online meeting getting set up. We're almost ready.
Okay, in this talk, very brief talk, I'm going to talk about the Animal AI Olympics, which is a competition that is now. I guess you are going to know it, so you will see. If you want, there's a workshop about this competition, which all the participants are going to discuss about their results and their specific solutions. But I wanted to talk about this competition since I think it's very interesting. It's new for the machine learning community in terms of complexity and things that want to tackle, and then it could be very useful, I think, for the Numenta work on reference frame and the absence break theory to use maybe this benchmark in the future to try out different implementations of the theory. So I just wanted to talk about this. That essentially the basic idea was to take these reinforcement learning agents and compare them on tasks that had been tried on animals in terms of cognitive abilities and simple tasks, if they could solve these kind of simple tasks as well. Because we have seen that some reinforcement learning algorithms and machine learning techniques have already super intelligence ability on some specific tasks, but on these even very simple tasks in the cognitive world, they're facing major challenges, and so the idea was to pit animals and yeah, this is the reason of the name there, Olympics, animal Olympics. So I guess we can just see this video is very short. It's a 2-minute presentation, a teaser of the competition. I just thought it was like short and clear, so I just wanted to show you that. But this is the victor on load and other tasks, very complex tasks. But that was an example of it. After a while, the dog can learn how to, go through that thing, just changing the angle of the stick. And so in this video, there was like a teaser on this particular task in which you can see an agent that has learned, let's say, how to do this exact task. But in the end, the competition is not about this specific task. It was just a teaser. PPO. Yeah, it's the algorithm. Let's say the state of the algorithm for reinforcement learning, model 3.
So virtual agents, virtual environments.
Yeah. But it turned out to be not the competition was not about this at all, or similar tasks. So we are going to see that. But it was just to understand the idea behind the competition. Right. So that's it, I guess. So the competition, I think it's one of the biggest and more complex competition that has been ever organized in the AI community, because it was completely based on a server-side pool of machines. You could train your agent on offline, but then you could upload this agent, and it had like 10 different categories of tasks. For each of those, you had like 30 environments, 30 let's say environment in which it had to be tested, and so the complexity is.
So the idea that the agent has to solve all the different tasks.
Yeah, so that was an interesting new idea, that you were evaluated on a synchron ranking board, in which you had the score for each different category of tasks, and for each of these categories you had like 30 tasks that you have to surpass in very different configuration. So it was very.
But you're being scored across, your score is across all the tasks.
Yeah, in the end, you compete with other participants across all the tasks. Then there are
The single,
prizes maybe
a
on
single entity. I mean,
yeah, a single
train
agent is
without
uploaded there
without reconfiguration.
without any reconfiguration. Yeah, so that was quite powerful. And it was also very, very tough. We will see the results. It was very difficult to excel at the sum.
Is there any learning involved? I mean, so like, do you have to be presented with a task you haven't seen before, or are you able to train on these 30 tasks?
So that was a big, at least for me, was something I was very disappointed because the challenge was also advertising the idea that you have to adapt, and that this is something that in the continual learning is very interesting. So I thought it would be like a phase in which you do the pre-train and then you upload that, and then you guys learn the fine things. But it turned out it was not the case. The idea of the work competition was organized so that you don't do learning on the server, let's say, side of the competition, just testing your pre-trained agent on several different things. So the idea was, as always in machine learning, to have a training that is general enough to cover the entire space of possibilities, gain generalization, and then use that on many different tasks.
And there's no sense of how long it takes to train or how many repetitions.
No, in that case, just inference. You take the model and do inference with these.
But you use the inferences on the same set of tasks that you trained on.
Yeah.
The same environment.
The cool thing is that they were completely hidden. So you don't know the configuration
of the environment.
The specific configuration. But of course, it's like they say, okay, you can try this. They are going to be a bit different, maybe a lot in some particular categories. But the whole idea is that they are hidden, and you should come up with an agent that is general enough to cover everything.
Wait, I'm still a little confused. So you train on a bunch of tasks.
Yes.
Is the same task during inference?
It's the same task, but not the same environment, right?
There's
so maybe they can be changed
So
configuration.
30 tasks with lots of different environments for each task.
Yeah, now we're going to look at more specific into that. So you can, I can give you the slides, and there are all the interesting links here.
I'm just trying to get your summary so we don't.
Yeah, if you want to learn more about this, there is an official website. There's the competition website on Level AI. There's a blog in which there are many posts about more specifics about this competition. And then there is also a very big GitHub page in which you can find all the environments for training and testing and baselines to start very quickly with your own strategy. So this is actually what it turned out to be the competition. You can see on the left side, the image on the left side, it's essentially the arena in which everything has to happen. So the blue dot in the center, I don't know if you can tell that there's a blue dot in the center of the arena there, is the agent. So this is a 2D perspective, so from upside down. But in the end, the agent, what it gets is the image on the right. So it's a first person visual angle, 60% of visual angle. So what you get is this image, 84 by 84, the vector, velocity vector of yourself, so where are you moving and with which velocity, and the eventual reward that you get over time. And the objective is to collect food in different environments with real-world physics. So we're going to see that in this arena, there will be many objects, but essentially the goal is to reach these green dots floating around that are foods, and we have to collect them to close the episode and win the episode. Each episode is task.
So this is one task.
So you're gonna face 30 of those. So for each category, so you have 10 categories.
This is one category. Collect.
Yeah, this will turn to be the first category in which we don't have objects at all. We have just random food.
I'm just wondering if other things can be. Is it all about collecting green dots? Or
yeah, the objective is just that one.
For all of them.
Yeah,
it's like a game of snakes.
For all
30 tasks.
All 30 tasks.
Yes, but there are so many things around you that will challenge that.
All right, let's move on. Let's see the challenge.
Yeah. So for example, you will have many different objects around the arena. Some of them are movable. Some of them you can't move. So for example, you have ramps. You have it's the Italian caption. It's it's in another part. So you have many walls. You have tunnels. You have ramps. And then these are you cannot move them. It's too heavy for any
Some of them are transparent, so you can see what's behind.
Yeah, exactly. So and they can have different colors, but then there are also objects you can move and they have different properties. So they are more heavy. You have to push them with more velocities to move them. You know, a lot of interesting things you can do. Then you have some areas in the environment that are giving you negative rewards, these hot areas, and then you have places in which you just cannot go over. They will kill you, and you lose. And then you have to pick these green goals. This is the food, and then there are also mortal objects. Yeah, you don't absolutely have to pick up.
The sphere of death.
Yeah, it's actually what it says.
The rights are horrible, like Trump and the
And then you have also rewards that are not going to close the episode, but are just going to give you some rewards points. So you can grab them, but it's not you're not winning the episode in the end. And these are gold spheres.
Mm-hmm. Are the gold spheres statically positioned, or can they move around during the task?
Well, that's a great question. Actually, you have if we look here, there's the actual definition for all the possible objects. So, for example, there in this case they do also this distinction.
You can close it too.
Like this. So some of these objects, they are moved. You can move them as well.
Right.
So they can, if another object touches them, for example, they can move. Some of them, in other cases, they are just fixed.
So give me, what are the different, I mean, you said there's 10 categories? Or 30?
Yes.
Well, give me just no, I don't need to care about the details.
Okay,
I just
okay,
want
let's
general
go.
Get a
idea
sense
the
of
Let's
it.
go
Right?
ahead.
Yeah, the details here we shouldn't be going through.
Yeah, just to give you an idea of the objects so that we can understand how we can interact among each other. So these are the 10 categories that we had to consider for this challenge. So maybe we can go directly here with the definition of that example.
Can you just talk about it?
Yeah, I mean, it's useful.
You already talked about one, collecting food, right?
Yeah, exactly. So
okay, let's go on to the next one.
So this is just collecting without any object. So no other things around, and just the green dots that can be randomly put around the arena, and you as well as a different spawning position inside the arena as well. Then you have the second task in which it's to challenge the agent ability to take all different choices, right? That can be more valuable than others. So, for example, this is a quite simple case, but you don't have to pick the red one. You have to pick to maximize the rewards. In this case, you have to pick the gold one and then the green one. You can imagine there are thousands of different configurations here. Maybe in some cases,
sure.
Okay.
Let's keep going.
And then we have the obstacles, one in which there are some obstacles inside the arena that you cannot move and you have to move around.
Keep going.
Then the avoidance one, in which you have to avoid.
Don't go there.
Yeah.
I get negative things.
That's spatial reasoning. In this case, it says, but I don't know if they already published the final test environments, so I can't really tell what the agent in the end was tested about. But because they asked each participants to just figure out what they thought it would be useful for this kind of task without giving much more details on it. So it says just its spatial reasoning is to understand spatial affordances in the environments and use that to your advantage. What really means, but
like you have to move a
ramp
to get to something and climb up it.
For example, maybe understand that the ramps is going to change your velocity, all this stuff.
Yeah. Okay.
Then the generalization part is just changing some very superficial thing of the objects in the environment. So, for example, changing colors of the wall, and to test that if the agent is generalizing across different situations, but not in terms of colors of the objects you want to collect, like the red sphere, the green sphere. They're gonna be like always red, green, and yellow.
It's a pretty weak form in generalization.
Yeah, it's a weak, I would say
Yeah.
so. Yeah, it's
Okay.
like- but for state-of-the-art reinforcement learning algorithms, it's already well.
A challenge, yeah.
Yeah, it's just
Okay.
a shot. Then this was very cool. It's called internal models, and the idea is just to switch off the light in the environment so that you don't get essentially the frame, the image for a specific time window into the episode. So, for example, you have a few frames, and at some point you're just gonna have black frames.
Right, you need to kind of be, if you want to make use of the time that you're blacked out, you
Yeah,
kind of need to
exactly.
predict and act
Yeah,
on
because
what you might
I
know.
forgot to mention, you have a limited amount of time to finish the task.
This starts getting useful because this time you start getting into the whole idea of building models. of the
Yeah,
environment,
exactly.
Right, so it's no longer just feedback.
Yeah, it's attention and so on.
Yeah, that was why I brought it up. So this was very cool to build an internal model-based learning. That is also a goal of, I would say, recent reinforcement learning literature. Then there is this that you can see here. They are not suggesting any training. They don't give you any details about this other stuff. And I mean, you will tell that it's something.
Don't you need object permanence to solve the previous one? I mean, you have to know things are there even though you can't see them.
Yeah, I mean, you could also just move around to the point you see them, and maybe this. I think that,
No, if you solve the previous one,
Yeah.
the whole point is not to do it randomly, right?
So I don't know the specific task in which this object permanence is tested, but maybe there is an object. Maybe you see something, then if another object is moving and covering the object, you should be able to just move around that object and go straight to the
Alright.
thing that you already have.
It seems to me that if you solve the previous one correctly, then this one comes along.
Yeah.
for free.
So we see that it seems like in terms of results, if you look at the results of your own agent trained, it's complex. It's a very complex task. I don't know why, because I haven't seen the tasks, but it seems to be much more challenging than the other previous tasks.
Good.
And then we have the advanced. This is instead. I don't know why they included here, like in a very. It's like it seems to be a very complex task, but it isn't in the end. Like it's called advanced preferences, and it just the preferences category we have seen before, a bit more complex. Maybe you have more complex choices, but
This is not obvious. with this.
but
Okay.
and then we have this one causal reasoning, in which the idea is to better understand how things in the environment affect each other, and the idea that they want to understand causal relationship between your actions, the world, and how objects.
This also seems like it would be, if you build a model world,
Yeah.
this would come with that too.
Yeah, absolutely.
So I'm surprised at the order here because it's going more difficult. It seems like once you built an internal model of your environment, then
Yeah.
Include causality, yeah.
Yeah,
Yeah, absolutely.
includes permanence of things you can't see, you know are there, you can predict them. Yeah.
So these are the 10 tasks. These are the results of the final results of the Animal AI Olympics.
Is this held at one time? Is it like
So it was open for a few months.
yeah, and then
and
there's a
people-
deadline and then people submitted
Yeah.
it. And when was that deadline? How recent was that?
The final deadline was a few weeks ago.
Okay, so this is recent results of,
Yeah, these are the last
I
results
just
of
don't
the
know how recent it was.
competition, in which more than I think 60 teams participated in the end, and this is just a few of them. I couldn't fit the entire table in the slide.
there's different names here. There's number 9 is numerosity, which wasn't the title you showed.
I don't know this is I don't know, maybe they changed the naming convention, but
Okay,
yeah, they are the same tasks that I described.
I'm just saying it's also numerosity.
Yeah, right.
Something different, and now the scores are better.
No, this is the what was called before the
Advanced
multiple.
preferences.
Yeah, exactly. So that was saying that it's if you look at the results, this is the percentages of test episodes surpassed for each category.
Isn't that, there's no success or failure, it's a score, right? So,
I think it's a percentage here.
Percentage of
It's
what?
a percent of success over the test
but
episode, number of test episodes. So for example, if you
I thought, but some of these are just, they're scored based on, I can get all the food, but how is this?
there's a threshold after a while. If you reach the end goal, I mean, you have to reach the green goal in
I mean, so since it's a score, a linear score on some of them, I guess they put some number, or some numbers that that's 100% or something like that.
So
It's either, I think if you get the food in a certain amount of time,
Yeah.
then it's 1, otherwise it's 0.
Hey, you guys.
yeah.
The authors of the benchmark are watching. If you have any questions, just ask.
Cool. Okay, so these are.
And I guess it's to get the food, you need to solve some of these issues in order to be able to even get the food. And so for number 8, if you want to be successful in getting the food in a certain amount of time, you have to solve the object permanence problem.
I guess, is it a time dependent?
It's a time, that's what it sounds like. It's like you have a certain amount of time to.
Yeah, you have a fixed amount of time.
Of steps, yeah.
But like the food, I'm sorry, we could have a direct conversation with the authors. But you know, if you're getting the food, but you also need to get the bonus points from the gold spheres. I mean, if you don't get all the bonus points, then you fail, or is it like, you know, is it a time reward thing?
So it's I don't remember exactly.
Well, it's not that important. I guess I can't look at this chart and understand what those numbers mean. I assume higher is better.
So
But if I look at causal reasoning, they're down in the 1% range. I look at the numerosities in the 50% range. I'm like, well, there's a big difference there. I don't really know how to judge the skill of the agent under those different tasks.
Yeah, you need to see some video, right?
Well, I know, I just need to see how the scoring is actually calculated. And it's not really a detail I care to know right now. So, but it's just, when I try to read the chart, it's kind of hard to read it without knowing that information.
Yeah, so for that, I think we can just consider this as a percentage of success over many different.
Yeah, I know that. I just can't, the number 1% versus 50% is meaningless to me if I don't know what success is.
Yeah. Well, we have to look into that because I don't remember correctly.
It's not important at this point in time. Just if you knew, great.
Yeah. So these are the results. I mean, we participated as well. I don't know all the details.
Who's we?
It is the University of Bologna team.
We're your team.
Yeah.
Okay.
So I just followed the essentially this graduate student that is Diego.
Were you on this team or no? Were you part of the team?
I was part of the team, but essentially much of the work was carried out by Diego Pergolini, who was doing his master dissertation on this challenge. We followed it with Davide Mattoni, so it was just a small team, and we got to the 9th place with a few approaches meld together. So essentially, we started with a model-free reinforcement learning algorithm, which was also the baseline of the competition, the PPO2 algorithm, proximal policy optimization algorithm. And so one of the tricks that we used was to essentially reduce the dimensionality of the input. It was important to have a better convergence, a bit more of generalization.
So what was your approach in doing this? Were you did you say we're going to try to solve all these tasks at once, or you just say no, we're just parse off for this first attempt, we're going to do 4 or 5 or 10 or 8, whatever it is, and then ignore the rest?
So that's part of the solution.
What the answer?
One of no, I mean it's one of the specific idea we use to participate in the competition. So the idea of curriculum learning, of designing different types of arena with incremental complexity difficulty, and use that to train the agent to improve the ability to solve the more complex tasks.
I guess I'm saying, did you actually try to solve the more complex tasks? I mean, I saw the super low scores on the highest one there.
Yeah.
Or did people, they said, you know, we're not going to try that now. It's beyond our
I guess mostly that. I mean, we focused on the first 5, I guess.
Okay.
Categories that was easier. And then from that on, we started to build moving towards that, but we couldn't reach good results as the rest of the community gets on the more complex tasks.
When the task is presented, are you told the category, or does it have to figure out what it's trying to do?
So you don't have the specific notion of the category in which you are doing tests.
Okay, so
you cannot exploit that.
So you have the specialization, it still has to decide which one.
Yeah, if you want that, you have, like in the last part, I said model specialization, in the
Right.
sense that it was, especially in our local tests, that useful to have to train the agent, multiple tasks together, but then to specialize on a single task. The policy on a single task, it was better. But you don't have the notion. You have, if you want to incorporate that, and we did it in the app, you have to, automatically infer what task are you solving.
That was what I was wondering.
Yeah, you don't have that. You don't have the label of
Oh,
task.
okay. But did you have to do that, or did you just say, as a test, we found out if we specialized it, we were better, but we still went with the more generic one in order to do the challenge? That was a question.
Sorry, can you say that again? Sorry.
So we when you mentioned the model specialization, that was like an offline test that you did
Yeah.
to see whether you did better
Yes.
results, but you went with the generic one, of
Yes.
the real challenge.
Yes.
Okay. All right.
Yeah, but then there are a few more tricks. I mean, we used our recurrent model that turned out to be important as well. So we have to account time
Is it true that the only behaviors that this agent can have right now are movements in directions? What are the other options it has? Like,
It can
it
also
doesn't have,
yeah,
it doesn't have a
just-
hand or manipulator or
no,
anything like that.
just like the
It just either bumps into things or moves things.
Yeah.
Is that right?
Yeah.
And if you bump into a reward, you get the reward.
Yes.
You don't have to do anything else.
But to move something, you bump into.
Yes.
Yeah. It seems like, are we ready for open commentary now?
Just 1 second. I wanted to show just a few videos on this. Okay, so yeah, and to conclude, reward shaping. Also, this idea that you have to put a bit of reward to incentivize somehow the behavior of the agent that you want to, that you want the agent to have. Like, for example, to improve exploration, we added a few shaping rewards to just, for example, incentivize the idea of moving straight in line. That's not moving around, random, or the idea that it gets more reward if it moves fast, like with higher velocity, something like that. It helped to improve exploration of the environment, to decide where to go and to move in direction. And then I guess that's mostly. I mean, these are more ideas. Maybe we can skip this idea of how we reduce dimensionality, but that's really important, I guess. And so most of the solution was providing a good curriculum and a lot of possible, as you can see, arenas in which the agent could learn how to solve the different tasks category. So these are just a few examples, but Diego did an amazing work in trying to put these in a straight curriculum, and then to move from easy arenas like the first ones in the right up corner, in the left right corner, and then moving to more complex arenas. For example, this one, just because I've seen it, you start here, and you have to move here and then collect. Be very careful without touching the red ones and collect these. Or this one is super complex. You cannot see the green one, and you have to navigate all these labyrinth up to that. Or here you have to move these boxes before to get to the world. I mean, there's a ramp here. You cannot see it through this whole configuration. I mean, it can be very, very complex.
How good were the best players at solving those kind of problems? So those complex problems.
The results. I mean,
just qualitatively.
I think that we are not anywhere close to the in terms of internal model, subject permanence, causal reasoning, it's up. It was way off.
Have they done a baseline where they give the human the exact same view and try to do it and see if they can do it?
But I can show you a couple of videos just to. Oh, what's up, Dave?
These are from the actual competition.
From our, for our trained agent, this is what the agent sees. So in this case, for example, there are a few red spheres, and it just goes there. This is easy. And here, I think it was like to choose a lot of yellow spheres just to get the reward, and then just later on move to the green one that concludes the episode.
Yeah, but that is weird based on Jeff's early thing. Like, how does that get scored?
Yeah.
If you get 4, if you still get the food at the end.
I think you have to get the food.
It's funny how
to conclude
the green and the red,
fast.
the green and the red.
Otherwise, you have a threshold after which the episode is considered.
Yeah, but you can do it fast and get the 4 circles and fast and not get the 4 circles. In both cases, you succeed.
Yeah.
But
Right.
the 4 circles would be better in some way.
Yeah,
Right.
maybe no, but maybe there are some cases in which you don't have the green one. I read before, you have just these yellow ones and you have to collect them all. Something like that is.
Yeah. All right, like just details
something
here. I don't
written
think we
down.
need to
Yeah,
know.
I don't
We
remember.
don't need to know the details here.
Hey, by the way, they say they're running human baselines next year.
Okay.
So to me, there's so many, benchmarks that I don't really care for. The thing I like about this one is at least the idea of building a model in the environment.
Yeah.
It's like the first time we're getting close to what brains really have to do. And the reason I asked about the body is because basically you're just all the solutions here can be solved with a hippocampus, right? Or an hippocampal complex. You basically have the body, its orientation, and one form of movement. Whereas I think, I'm not saying that these are easy to solve, but I think that's at least forces you to start thinking about model building, right?
Yeah, absolutely.
And then with the idea that you turn the lights out, then you have to sort of build this model in real time. That's the key thing about this, right? So that was a great innovation. I would just say, in the future, this could become really useful if you can get beyond that hippocampal complex sort of limitation, and then you can start saying, okay, well, objects have affordances themselves and behaviors themselves, and your body has different behaviors that you can, manipulations and so on, that have orientations and so on. So the basic framework could be extended dramatically to really encompass much of what we know the cortex does. Building on sort of modeling a lot. Now we're just modeling environments, but then modeling objects in the environment and modeling the body of the objects. I mean, that's really what it's all about, right? You're modeling your location, which is sort of the hippocampal complex. You're modeling objects, which is what pathways, and you're modeling your body with the where pathways. And so the framework could be extended to really do a great job. Where I felt like things like the old Turing test could never be extended properly.
Yeah, absolutely.
So this one at least has a good foundation.
Yeah, I totally agree. In fact, I prepared these for you.
Yeah.
So this idea that, the thousands brain theory can be very helpful, I think, especially for understanding object behaviors and compositionality, spatial temporal correlations, and sensory motor integration. That as well, they could as well be helpful for model-based reinforcement learning, and especially for these categories like spatial reasoning, internal models, object permanence, and causal relation.
I mean, it remains to be seen. Like the cortex builds models of the world and models of objects, and it does it in a certain way. And it's not clear that that's the only way you can build models. But it is clear you have to build models.
Yeah, absolutely.
So that's absolutely clear. I suspect that we're going to be much closer to the way brain does it than not in the end, but we don't really know that. But at least it's forcing you to think about those lines. I agree with you. It's a moving in the right direction for focusing on model building and real-time model building as well.
I have 2 questions. One is, what is the amount of result variability? So the thing is, of course, any individual, layout might be a, success or failure for your agent, but I assume that the variability is quite high. Just from the autonomous robotics courses that I've done where, you would set up a random maze and you have to do tasks and things like that. So I've done these things in the physical world, right, rather than the virtual world. And, to get a proper understanding of how good or bad your agent is, any individual environment might fail you totally. So how many of these, different cost categories, right, tasks do you then have to solve? I assume there's some averaging here.
I don't think so. I mean, for the testing part, you have, the agent is mostly deterministic if you implement it like that.
You're right.
So the idea was to have a sufficient number of test episodes to cover, the interspace of what you want to say that task is about.
Yeah, what is the sufficient number? I don't know.
I think that they had like 30 tasks, 30 different, environments. In which
30 different environments, okay.
Yeah, but the thing is, you bring up an interesting question because, we think about
Because you might just win because of dumb luck.
Well, or you might also exhibit sort of the catastrophic failures we see in neural networks today, where it works really well 99%, 98% of the time, but you can easily spoof the thing and fails completely. Which I think is why the human testing is an interesting question because, would a human ever get stumped just because you move something a little bit? Will this thing work almost all the time, but if the red ball just happens to be in this one spot it's going to fail because you spoofed it,
So if we have the creators on this available, I would love to ask my second question also, which is why not use highly performant, great physics engine existing game solutions
Well,
like
They do.
Unity.
Unity 3D does that.
Okay, cool.
It's great. It's just that
Because like to me, this sort of like I would want to put this in like Portal or something, like an established curriculum where we know exactly how people perform and it's challenging to us, right? And it has great physics.
It was really odd though that the red balls were just circles and the golden balls were spheres with the highlights. I didn't wonder why they didn't put that on
actions
that.
or shapes or objects. Yeah.
Made it feel like
They're probably both spheres, but one doesn't have any reflectivity or
I'm
it's
just
projects.
wondering why they did it that way. You're talking about the physics engine.
Yeah.
It had the light reflections thing going on with some of them, but
It just seems like like sort of cobbled together. That's why I wonder why not do something.
I think it's a
more
very
grand.
sophisticated physics engine, but then they're doing basic blocks world.
Yeah, right.
The problem is that you got like 84 by 84 RGB image. So in the end, all these details maybe are not that useful for the current state of the algorithm. So
It's a resolution issue.
Resolution, but also it's the interesting part was to understand how objects maybe interact among each other and the agents as well, not just about the details of the. I said in details, let's say, and I don't think they are super useful here, in which you have like not a large number of objects you have to distinguish and stuff like that.
Which do you think is more complicated, this or doing something like Dota? Which is a massive multiplayer game, lots of different levels and complexity. And you have other players, you have to build predictive models, you have to build world models. And
I feel like you're
all of
me on this.
No, I'm just wondering. I'm genuinely curious. I don't know.
No,
because there may be aspects of this that are.
All these games they try to solve in the end, they just reduce the dimensionality with a lot of tricks. They don't start from pixels, for example. They just have all the different
But OpenAI has this Dota player, which is one of the best in the world against humans.
Yeah, but
and it's a much more complex environment than this. And is this fundamentally different? Is this?
but again, the Dota version, I think it's just an LSTM, like 1 or 2 layers is LSTM.
We're talking about the implementation. I'm talking about the task.
does it actually learn a model of the worlds it's in and so on?
Well, it has to build a predictive model because it has to predict what other players are going to do and beat them.
But it could be.
And it's also this is also a game. You go and get food. And boy, this is exactly a game.
Yes.
Well, I guess the question I have is like when I think about what DeepMinds did with their the video games they did, right? And you can say, oh, they're solving these various video games. They must have some model of what's going on. I don't think there's any model at all in there. It's just basically it's doing this really sophisticated.
Well, the Dota is different.
Well, I don't know enough about that, so I'm asking the question: do they really have models? So they can say if it's a 2-layer LSTM, I can't imagine it has a model of the world it's in.
It's model free. So they use algorithms that are model free. So that's it. I mean,
that's a different use of the word model than what Jeff is saying. It's completely different use. Yeah.
Okay, I don't know.
But it's a complex world. But it's a complex multiplayer world, and the players have strategies, and you have to real time adapt to their strategies.
Do they actually? I mean, I haven't played these games, but I imagine if I play one of these games, I build an internal map in my head about what the layout of the land is, and where the obstacles are, and where I've been before.
I think they would have to do something similar.
Well, I don't know. It seems like they can if they're doing it with a 2-layer network.
Well, it depends how big the recurrent model network is.
If
it's a million networks,
unless there's some way of representing structure in a metric way, I don't think you can. It won't have a model the way I refer to the word model.
Right, but it may have learned that metric structure.
Hard to imagine.
Well, in the deep learning sense,
yeah,
right? In the sense that you extract regularities and things to hold on to memories that are necessary, right, to perform the task, but not in a sort of symbolic reasoning understanding.
Yeah, and so therefore you won't be able to generalize. If you don't have a structured metric model of some sort, you can't generalize from it. I don't know how you could.
Yeah, I guess my question is not so much about the implementation, but just about the task. Which task is harder? It's not clear to me that this is actually harder. I mean, maybe that every component you have. I actually genuinely don't. I don't know much about Dota either. So
yeah.
I think it's in the sense the one where you basically learn a model and turn off the lights. That seems generally harder than any other implementation of anything I've ever seen before. That really requires an internal model of the world. Other than that, you're just reacting to the things around you, but to move around in the dark and to know what you're doing and where you are, you literally have to have, grid cell-like representations of the world, metric representation of the world. I don't know if that can be done in those other games. I doubt it.
But I don't think you can, in Dota, I don't think you can just react to the sensory stimulus. I think you have to have some notion of the past.
Yeah, but how much of the past?
I don't know.
That's the trick. I guess that's I've come down to believe it's like say it again. You have to have some a metric space representation of the world to really do reasoning. And so that's what I liked about this, because when you turn the lights off, you have to have a metric representation of the world. I can't imagine any other way of doing it. Where if I didn't turn the lights off, I can always imagine saying, hey, there's the last flow of the last 3 seconds of behavior plus my current input will tell me what to do and better than other people. I can do it really fast and really well. But I really don't know what the hell's going on. I can't internally visualize what's happening. I thought that piece, the model plus the lights out, was the key component in this hard. That's what made it more interesting.
Did any of the models do well on that part, or which one was that?
I don't
like
think so.
Let's see.
Is that the internal models or object?
Well, it's the object permanence. I think which is the one where you turn the lights off?
7.
7. 6. But again, all right. So those numbers are pretty high. I don't know what they mean and how hard the problems were.
Yeah, right. It's just a blink, or if it's look around and now lights off for the next half hour.
But I can imagine one strategy just being, if the light's only off for a certain amount of time, just don't do anything. And as soon as it comes on again, then you start moving again. And as long as you're within the time
just
frame,
continue the previous action.
If the designers,
in many cases.
Yeah,
If there's
exactly.
an object in front of you, then
Exactly. So you don't really have to solve the problem. You can come up with some stupid hack that works okay.
if the designers are still online, and if you think about what brains do, right? We build this internal model of the world, but you can't manipulate the model from complete darkness because you've got your path integration errors, and they're just always going to be there. Right. So a way of extending this is to say, like, okay, I have a sense, like a vision sense. So I see this image. I can have a different sense, which lets me detect something very close to me. That's like my hand touching something. So if I have a model of this office, it was completely pitch black in this office. I can't walk around and do things because my path integration errors are wrong. But if I can just constantly touch, like I know I'm expecting the door jam here, where is it exactly now? I know exactly where I am. This desk here, where I know exactly where I am. Right. So you can extend it with that sort of 2-level sensory modality, where you have a internal model of the world, which on its own will never be sufficient because of path integrations. But you need to have it. Then another way of sort of like reorienting yourself and figuring out where you're all the time. That's what humans do. With other animals do. We just use small sensory inputs to relocate ourselves all the time. We do that when the lights are on too, but we don't take a picture of the world, right? We just look at little things.
But I did that, people do that all the time, and I've done that in like robotics competitions where you use like some infrared sensors to recalibrate the odometry, right? Because like the wheel counter based on your moving robot, right? It tends to drift, and like you don't know exactly what speed you're at, and so over time you're gonna need to like learn to correct for it, and you can do that by just taking other measures like infrared sensors and distance to the neighboring walls and things like that. Right?
So, but again,
that's a standard thing.
But in the sort of in robotics, they have this idea of building a world and modeling the world. Right? That's been around for a while. So I mean that's sort of what's the SLAM or sort of what you call it. So that's why I'm saying this is sort of like a SLAM problem. Yeah. But to extend it to solve, we need to model other things besides just the one space and the one environment. So we get back to modeling objects and modeling other behaviors in body sense.
I must say I'm a little disappointed that there's no actual competition against an animal, because it's an entirely virtual competition. Like I would much rather have I don't know.
I was disappointed seeing the dog couldn't get the stick through the barrier. I mean, come on.
No, but seriously, you could have a small robot compete with a mouse or a rodent, right?
No, but the idea is that all the tasks has been designed to be faithful to some other experiments carried out before with animals, right?
Oh, I see. Okay, so
I disagree with Floyd. I think it's better that you don't bring in the animal stuff. It just messes it up. it's like Turing bringing in humans. It just messes the.
What kind of messiness do you want?
I think this is nice to have a structured environment where I think what you want to get is the essence of learning and model building, and not the specific,
It's just the name.
of individual animals and individual capabilities, and mice have different eyeballs and dogs, and it's just like.
But if I can just come back to the question of Subudai before 1 second, I was thinking about that. And I think that it's very complex to get the real complexity of the two tasks. So I cannot talk about that. But I think this challenge is very useful because it's pointing towards specific directions that we care about, right? So
It's
it's
more
it's
much more structured.
Yeah, it's much more structured. So we thought that, okay, maybe they are useful, maybe they are not. We don't know that. We have to look into that. Instead, in this case, we're just saying, okay, these things are important. We have to look into that because they're part of the main metric and evaluation part. So that's
It's funny,
what I like.
Bringing up Florian's comment about animals. I find it odd to call it the Animal AI Olympics because it's really not about animals. It's about world model building. It's basically extending beyond today's. I mean, because we're really not talking about animals doing here, and we can come up with the extensions of this model that have nothing to do with particular animals.
But the thing but I think it's more an inspiration. I mean, the thing I like about it again is it's not focused on humans. It's like even animals can do these kinds of tasks.
Yeah.
So let's just focus, and
Well,
that's sufficient for intelligence.
When you first hear the title, you think it's something different.
Yeah.
I guess that's what I meant.
Yeah. All right. Well, we can get over that. You learned the like a word.
It's a cool battery, and it's awesome to see that people are standardizing these things, so we don't run into this problem where people cherry pick their problems all the time. Right? And that's wonderful. And everybody measuring by a baseline.
Yeah. But I do think it's really hard to get serious about these things unless you have continuous learning. Without it, it's just fundamentally you're still training on 30 different games ahead of time and then playing the same 30 games.
That's where the model building and the lights off thing. You can't do that unless you learn during the task, right? You present a new environment, you have to look around and explore the environment. You had to learn that environment at that time, and then the lights go off. And
I mean, maybe you can do it without mechanisms with this.
I don't think that's.
I know, but
I don't think it involves learning.
Sure. How else can if I don't learn an internal model? I have to learn an internal model.
No, you just have to.
map.
It's just for a few
The map
frames.
is a model.
No, it's just for a few frames.
Well, okay. So if it's just for a few frames, it's not as useful. My point is, it should be like, okay, you learned this world, and now you're in it in the dark, and you have to solve the problem. Well, they could do that. There's nothing. There's nothing in that says it's only offer
But that
a few
performance
frames.
would be 1%, like the causal reasoning.
All right. To me, that gets okay. So if it's just for a couple of friends and it's not as interesting, then you're.
That's clearly the most interesting task from our perspective.
It's not totally obvious to me that you need to change your ways.
I just think changing. It's just saying you have to learn. You're presented an environment. You have to learn that environment while you're moving through it.
In principle, it is possible to do that with just cell activations. It's all in the dynamics of the.
Well, I didn't go down that level. I just said that's I would.
What do we mean by learning? What do we mean by learning?
That you've learned. Let's put it this way: you've just learned an internal model of the in real time as you're exploring around. I agree, but I didn't say that could it be a temporary dynamic representation versus a permanently learned representation.
Okay, so it can do the temporary dynamic.
I think so, but I don't think it would. I think it'd be more likely. I think there's a limit to what we can do in those temporary ones, right? I mean, imagine I give you a complex environment like this office, and you're allowed to walk around in it for an hour before I turn the lights off. Well, I don't think you're going to keep that you're going to keep that in synaptic weights and maybe the very fast learning stuff.
Yeah, I was thinking maybe that's short term synaptic plasticity.
Clearly, I mean that's what it has to be.
Blurs the question of what learning is.
I mean, it's different than just saying quickly memorize with the location of several things around the table, which could be done perhaps in the dynamic state. But to really build the model, like, okay, I'm going to be presented this, dropped in this room later today. I have an hour to learn this or 20 minutes to learn it. That is going to be in synaptic modifications.
Well, apart from this specific category, I mean, I think it's obvious that you need continual learning for, if the reward change, if the food shape and color and whatever changes, the objects are not the same anymore, the dynamics of the environment change. So, I mean, all this stuff is not.
I don't know. I make the distinction because, changing what color the reward is, to me, is maybe it's continuous learning, but to me, continuous learning, it really boils down to I'm learning a model of the world and I'm continuously updating that model. And it's much broader than like, hey, the green balls and now the red balls.
Yeah,
I mean,
that's just a.
I mean, to me, to me, that again, I keep coming back to the whole idea of model building in the world is what the key core of this benefit of this thing is. And learning that in real time and as you go seems to be the essence of intelligence to me.
I think the generalization thing is so that they can limit the thing, saying just go toward the the green, as opposed to, okay, there's other properties that are associated with this thing. There's roundness, there's this, there's that, and then you basically have to combine all of them, to solve it in a generalized sense. So
Yeah, but you can't. I'm making a distinction between, let's say I like the taste of, some food, and now tomorrow that food tastes bad. So yeah, I have to change that part of my world, but it's pretty minimal. I mean, it's a very sort of point change as opposed to really on the fly learning the structure of the world in some deeper way. I'm trying to make a distinction between simple. I thought that the examples of generalization were very, very trivial. I didn't think they were very interesting. To me, generalization would be like, I can be any kind of environment, it doesn't matter anything, and I'll learn the structure, and then I'll be able to act upon it.
Okay, so let me take the slight opposite. I think they were trying to do that to eliminate some of the simple strategies, and have them fail. Now, you will say that there are higher order strategies, in generalization than that. But I think some of these things were to counter specific, simple-minded ways.
Yeah, okay, that's true. But the real problem with generalization, if I've come to understand it, is you've taken a system, you've modeled it in this metric framework. Now you can use the behaviors in that framework in a different situation in that framework to solve a new problem. So a different place to a different destination, and the behaviors to get there. Which is a much more deeper sort of generalization that can be applied to any kind of concept.
I agree.
Okay, so if you want to call it a simple generalization, that'd be fine.
Yeah, I think they were targeting to kind of punch out some of the simple strategies, so that people would look toward.
Yeah, again, if you say simple generalization, I go for it.
Okay.
But that's a pretty. Generalization is a much more sophisticated problem than the examples that showed. Okay, did we?
Okay, I think we're on our hour. You thought it would be short, huh?
So those cooking timers, like the baked cookies.
Oh, yeah. Oh, we can have
Think of hourglass.
Yeah, those are kind of cool.
Kind of fun.
The chess.
Yeah. Oh, chess time.
All right, I'm gonna change to show my webcam, and I'll show the whiteboard. Okay, I guess.
Do you want these?
No, I don't need it. I'll just turn it off. Okay, I guess we'll just move right on to the next topic. My motivation right now, this meeting is going to be mostly a review of things we've talked about over the years, not recently. Also, it's more things we've talked about like in this room, but not actually. We haven't dived into some of these details in our papers at all, to the best of my knowledge.
So you're saying this? I should recognize everything.
You should recognize everything I'm talking about. My motivation here is I want to understand the usefulness of sparse representations, sparse activation, both in like the brain and machine learning. And today specifically, I'm focusing on the SDR math, on the properties of SDRs, which we focus on. Just making that distinction because there are plenty of people who write about sparsity, who write about other reasons for it to be beneficial from a statistics perspective, from an energy perspective, all sorts of things come up. But today I'm mostly just focusing on where the SDR math fits into our models we've worked on over the years and trying to figure out where it then fits into deep learning, into machine learning. So something I'm gonna use some terminology that Jeff has used before in an almost apologetic way. So there are kind of two types of SDRs that in our models like spatial pool or temporal memory, all of our various things. I'm putting in my terms, semantic SDR and symbolic SDR. This is how I've thought about them for a while. I know Jeff has said like internally, sometimes he calls them dense SDRs and sparse SDRs, these two things, but we've never actually publicly said like those are what we call them. Those are just like informal names. One of these is like the output of the spatial cooler. Here I'm showing you some sensory input. Here I'm showing like you have a part of a coffee cup coming into your retina, activates a set of mini columns. And the set of these mini columns is a sparse distributed representation that has certain properties where similar inputs map to similar outputs. The representation that's activated here is going to be similar but not the same if another input comes in that's similar but not the same.
So overlap implies semantic similarity.
Yes, yes. So like these SDRs overlap to the extent that they're semantically similar. So I call it semantic SDRs. They have the overlap property. A lot of traditional neuron receptive fields fall into this category. Here I've drawn essentially a Gabor filter, and how this unit or perhaps the set of units might respond to this input that's like on in the center and off around it. And in my mental model of artificial neural networks, they're kind of this stacked on top of each other. They're these types of units basically on top of one another.
Except typically they're pretty dense.
Yes.
Yeah.
Yes. Yes.
Denser, denser than the dense SDRs that we use in the
And then you start losing the semantic abilities. I mean, right?
I don't know.
Well, you do because one of the nice things about if it's certain, you have to have a certain amount of sparsity because then you need a way of representing two things that aren't semantically related, right? So if we did a 2% SDR or something like that, then you're, I have 100 bits active. Well, there'll be on average, 2 bits the same. And you can say that's the null.
Yeah.
That's the null hypothesis. That's like no semantic overlap.
Yeah, good point.
If you have a lot of density, you're always going to have things overlapping. There's no way of saying,
Well, the way they would do it in that case is that just the Euclidean distance or the dot product between them is small, or the Euclidean distance is large, or there's other geometric concepts.
But it's not just overlap.
Not just overlap.
Yeah, but overlap is a very useful method. So
Right. Yeah. I'm not disagreeing. I'm just saying there's other methods they might use to say, oh, these two things are very different.
Okay. Well, in our world, in the brain, I would say that you wouldn't want this to be very dense because we're just relying on the overlap property.
I think there's another issue. Well, I actually think those two are very similar.
Are you going to talk about the second type?
Yeah, I can wait until.
Okay.
Well,
Sure.
I think of this.
That's right, because I said, oh yeah, there's a clear distinction between those two. Now you're gonna
So I'm ready to jump over. I'll point to this at some point in the future. Now the second type are these essentially random SDRs, where sometimes they're pseudo-random, like the temporal memory will take this non-random SDR and randomly sample it essentially, and get something that I think of as being like a symbol, as being this discrete thing that does not any longer have this overlap property. Instead, it's more like a random code that just never overlaps with other random codes virtually. And this is where the SDR math comes in.
I know exactly what you're saying. I think the word symbolic is somewhat misleading because I think most people would think of a symbol as having some sort of semantic meaning in the world. But, I don't know what to call it. I don't want to call it a random SDR because it's not really random. It's a random subset of the semantic SDR.
Yeah. I mean, the way I link the two is that I think of the left as a union of those.
Yeah.
So it's not. This is not just random. It's basically saying I don't know which of those are active right now.
It's
a
specific subset that's chosen randomly, so it's not. So I think whatever we want to call it. I'm just pointing out the word symbolic is misleading for a lot of people.
Okay.
Right. So I don't know what the right word is.
Yeah, and it's
we
not
can
random.
go with it for now. Just
put quotes around it.
Yeah. It's the other one. It's the subset. It's the component.
Yeah, and it's interesting that this information that's on the left is still there on the right.
Yeah.
Right.
It is.
It is and it isn't.
It is and it isn't. So let's get to that because I think that's the key. That's the key problem we haven't ever resolved.
And here, okay, sure. Here, though, I'm more focusing on the randomness. For example, when we make use of this property elsewhere, for example, here I'm showing pooling of a set of features at locations into an object. These we just call them random. The object SDRs, at least in our models, we just generate. We just let a random set of cells activate and call those that object SDR. And so to the extent that we treat these as if they're random.
Or the way to think about it is, if I look at those active cells in their mini columns in that physical location, then they maintain their semantic SDR property because I have the mini columns there. If I just look at those, if I just take the axons of those neurons and project them someplace, any place, and move them out of the mini column, then I've lost the original semantic meaning. It's just a bunch of cells and some small subset are active, and I have no semantic meaning at that point. It's only when they're physically located in the mini columns do I have the ability to extract out the symbolic or the semantic meaning, which is it's just a funny thing. So there's a balance between like what the neurons themselves represent and what the mini columns represent. Anyway.
Yeah, so I would say one interesting topic is how do you get the semantic meaning back? That's a little tangential to
Do you
what
think
I'm
you can
presenting.
get it? Do you think it's possible to get it back outside of the mini columns themselves?
Let me think. It's funny. I was saying that's a tangential topic.
Oh,
You're
you're
going further now.
okay.
Uh,
All right.
I
I've never seen a way of doing it. Okay.
We can come back to it.
Yeah.
So here I'm bringing up just this whole set of mechanisms that we've based on these sparse SDRs that often these mechanisms can be depicted as graphs or as circles with arrows connecting them with like, for example, sequence memory, X, B, C, Y. I've used little double primes to indicate context. And then it depicts, everyone here knows that this is a picture of voting between columns on objects and having associations between these sparse codes. Maybe I should point to something else, but sparse codes here and sparse codes here, and building a voting mechanism on top of that. All of this very much takes advantage of the SDR math. And when I'm saying SDR math, I'm just making the simple claim that I'm relying on the property that two random sparse codes are super unlikely to overlap.
That's true for both.
Yeah, I mean, the math applies on the left too. It's just that the numbers.
But random
are
sparse
different.
codes don't ever happen. They're
Well,
the left is a whole different
if I
world.
did take a random
I
set of
don't think so.
columns,
I think you can apply it to the left.
On the left, like so, I'll read what I wrote. So, given two inputs, semantic SDRs, that semantic SDR representations from, for example, a spatial pooler or from a feed-forward artificial neural network, they overlap to the extent that the inputs are similar, and that's what decides whether they overlap. These sparse SDRs, these other ones, they're either like at the representation level, they're either totally different or totally the same. And these random population codes, the fact that the codes are random, they can take advantage of the SDR math, the SDR.
you're talking about like the union property, when you say SDR combinatorics.
Combinatorics is just another way of saying SDR math.
What else is in SDR math besides overlap? Anything? I thought you were talking about union.
Everything's based on that. The fact that random sparse code is unlikely to collide with another sparse code or set of sparse codes.
I think that's still true there. It's just that the probabilities are lower because the numbers are lower. If you take two random inputs.
You're just saying numbers to the density or how dense it is, or.
Well, I'm saying if you take two random inputs and feed them to the spatial pooler, the chance of overlap are pretty low.
No, but these are two random inputs. True. That has nothing to do with the SDR math, though.
But that's what the SDR math says. That's literally what it says. Given two random inputs, what are the probability of high overlap?
Okay.
I'm not sure we're actually arguing about anything meaningful here.
I think there are like these two universes where like when you
I think there are
Neural
these two
networks.
universes, right?
Yeah.
There's the semantic versus the non-semantic, the less sparse, the higher sparse. There's things you can do when you get more sparse that you can't do when you're less sparse, right? So,
I think the fundamental thing is that similar things don't have any overlap in the right world here.
yeah.
I think that's a separate issue from the math, but it's
Right.
But I think that's a fundamental distinction between these two.
Yeah.
So that is well known from the brain and well studied under the topic of dual process models of recognition. This idea that you have brain areas that are capable of computing something like a global match because their brain representations are overlap based, so similar inputs generate similar activations, and so you can do things like computing a global match, so things like familiarity recognition, whereas more sparse representation, let's say post-dentate gyrus in the hippocampus, where you get super sparse representation that have like basically no overlap whatsoever, can do things like full recall and contextual memory, and that's why they're important, and that's the other mode of recognition.
So it's interesting because, when we came up with this, there was no thinking about this as these ideas were already out there. I wasn't aware of them. It might have been. Just wasn't aware of them. This all came about because we were trying to solve a specific problem in a cortical column. But I would agree with you, these must be properties everywhere in the brain. But I think what we did here is we in the cortex at least, we assigned them a very specific physicality of this idea of the mini column and the individual cells in a mini column, which I don't think, I'm not sure if that exists elsewhere, but in the hippocampus or anything like that, maybe it does. I'm not sure. I'm just pointing out that I'm surprised to hear you say, "Oh, this is well known." I didn't know. So,
well, I've studied it in specific because I've been looking at it's a common memory task, right? To be able to, on the one hand, be able to do familiarity detection. So on the other hand, to distinguish lures from full contextual memory.
So I felt this is a general problem that we have to solve everything we do. We go in between these two, and the sequence memory task sort of showed it in spades. It really exposed it in one simple task. They exposed this problem. And the way I used to think of it is like, well, in some sense, I have to have an input, which is the same input. I have to represent it differently in different contexts. But it's the same input. So at one point in the brain, there's representation. It's going to be the same for the same interval, and the melody is always going to be the same. It's the same input. But at another point, I have to represent uniquely. So how do you go back and forth between these two representations? And so that was the mechanism we came up to do that. And it seems like a very, very fundamental problem. But I don't know where you're going with this, Marcus, but the thing that always, the thing that's always puzzles me is that once you leave the mini column, you've lost this. I don't know how to get back to the semantic meaning again. You suspect maybe there's a way. To me, the physicality of the mini columns was the suggestion that that's where this has to happen. So somehow the mini columns are a way of going back and forth between these two representations. We've only talked about going one way, going from the semantic meaning to the more sparse meaning. We never really figured out how you go back the other way, but it seems like it must be somehow.
Yeah, that's why hippocampus is a loop, right?
Hippocampus is a loop.
I mean, like
this doesn't
out of entorhinal
happen.
cortex back into entorhinal cortex. So you have a reasonably dense distribution first, then you enter as extreme sparsifier with the dentate gyrus. You encode in a super sparse medium where you get these, symbolic sparse SDRs, which are extremely orthogonal. And then the activation actually loops back into the exact same entorhinal cortex.
Physically do that? I mean, what is the physical structure for bringing it back? I mean, I can project up there, but I don't want to have to learn all that. It's like saying, imagine I'm going along and I've learned the melody, and now I'm going through each individual note in that melody has its unique representation in the universe. And now I want to go say, oh, I want to predict what I'm going to hear, the interval I'm going to hear for the next note. Well, I don't want to predict that sparsity thing. I want to predict the semantic thing. So I I have to bring it back into, somehow I have to go from this very sparse coding back to a mini column coding so I can predict the input. Anyway, this all happens in a cortical column, so maybe it's thinking, and I would argue that now we think that everything that's going on in the cortical column is also going on in the hippocampal complex. But I would challenge you to explain how we do that. How do you go from the, this projection, this sparse thing can project back, but how does it recreate that structure? That's not obvious to me.
So I'm going to try to bring it to what I wanted to say, and then I can play around with
Oh,
that
you had
topic.
more words, so I thought you were done.
So so here I drew like this is essentially the activation of each unit, and in the spatial pooler these would be binary, like either here or here. It's all zeros and ones, but they can fundamentally be looked at in this same way. With these types of networks, it's like each of these could be thought of as being sort of like a Gabor filter or something more complicated, but probably the first layer is something Gabor-ish, something like this. As an aside, even the spatial pooler, which doesn't have inhibitory feed-forward connections, could still learn something like this through the lateral inhibition. But you can think of it in these terms. Each of these is something like a Gabor filter. What I'm saying is that when you pass in two inputs, I just drew these two little pictures. If you pass in two different inputs, if the output is dissimilar, it is because the inputs are dissimilar. It's not randomness hasn't come into this.
Context having come into it, right?
No, that's a separate question. Yes,
No.
yes. That context will make it where they split.
Yeah.
But here I'm bringing up the fact that just because there's this huge representation space of things that are possible, isn't the reason that the outputs are different. The outputs are different because the inputs are different. They're each a set of these filters.
Yeah,
it's a different explanation.
Yeah, I think we all agree with that, right? Was this
I think like so far up to this point, the SDR math hasn't played a role. It lives in this world.
I don't know. I guess I don't know what SDR math means.
It's using the property that these activations are essentially separated from their semantic overlap.
That's SDR math.
But no, I don't know.
SDR math.
I guess that's how
SDR math is
SDR math says that two things don't overlap; they're different, and if they do overlap, they're semantically the same. But you can't get that over here.
Yeah, if you live in a universe where every representation is just a random set of cells, SDR math totally 100% applies. You can form associations between them. You can pool them. You can activate unions of them.
Yeah.
You can do all of these tricks with them.
Do you consider overlap part of the SDR math? I guess not.
The overlap property, the semantic overlap.
Yeah.
No. I think that's
To me,
something.
that's part of it. I just didn't know.
Yeah, I guess it's a definitional thing. To me, I'm thinking about the equations I put in my paper, and they apply to both cases.
Yeah.
But if that's,
So I there's nothing arguing about
apply.
semantics.
They don't apply to the
You
scalar
excluded
case.
the overlap property from SDR math. Fine. I wouldn't have done that. So that's my confusion, right? That confused me because I consider that one of the most important math properties.
Yeah,
SDR.
that is what the math does, is it tells you the probability of overlaps.
So we could just let's not get hung
Or
up.
random inputs.
Let's just not get hung up on that. I think we all agree about the details. It's the labeling. Which
The labeling is.
right.
Yeah.
There's a property that occurs here that doesn't occur here.
Right.
Right.
Yeah.
And there's a property that occurs here which is harder to get here, like unions, things like that. It's harder.
And I guess there's a very actionable point here is does the SDR math apply to artificial neural
I was trying to avoid using the word
Does the
SDR math.
combinatorics, the whole random samples.
Well, if that's how you're defining it as random samples, yeah, there's no randomness over here. So I guess that's the trick. If you call SDR math randomness, then fine. But I guess that wasn't obvious to me what you meant by that. To me, the SDR math is everything we did with SDRs. It includes the overlap property. If you wanted to define it differently, only the things that apply here, then that's just a definition issue. We shouldn't get hung up on that term. We disagree with the detail. I think we're all in agreement about the details.
So maybe the question is how many properties that it can have. I mean, that we're could be valid also in this one without, these ideal having random features. Right, so is this the main question? How many probabilities that we know that work in that world can hold in this one where you don't have,
Well, I can take a stab at that. In this world, you can really imagine doing a union of SDRs up to some number, not a hell of a lot, but some, and it works beautifully. In this world, it's harder to do that. And I'm going to argue in a moment why it's even harder than we think it is. But in this world, you have the semantic overlap property. In this world, you don't have the semantic overlap property. So those are the two things. That's the distinction between them. That's how I would view it. I want to mention that over here, we've always viewed that the spatial pooler as being binary, but we also know that that's not true. We know that if you look at the minicom activations or the cells in the minicom activations while you're showing a sinusoidal grading or something like that, that there's always like a distribution. It's always like like that, and there's always columns that are. It's always a bump moving around. It's not It's like that, and we also know that's what it looks like in the grid cell world too, and. So it seems to be in this world, we really have this sort of bumpy distribution with some of the spilling over to adjacent columns or adjacent representations.
Where is that one is perfectly sharp?
And this one is perfectly sharp. And so we've never dealt with this issue, but it's clear, it seems, I used to always wish it away, like, well, maybe it's not important, maybe it's this and this and this. But now that we know that grid cells look like this too, or orientation cells look like that too, that it feels like, okay, maybe that's a fundamental nature of this representation here, which we didn't model in our spatial pooler. But you don't get that over here.
Right.
And this property makes it harder to do unions too, because it's just, it just becomes harder.
You challenged me how to do this. May I propose a solution? Like to do that back and forth.
Going back to go from here back to here.
Right, exactly. Because I obviously
I don't want to have to learn
it. No, I just want to propose a mechanistic, biophysically compatible, idea about how to do this, right? Because I've actually built models that implement this kind of idea. So my very first paper in Frontiers of Computational Neuroscience did something very much like that, where I had a distributed cortical representation, and of course, yes, my representations are much more closer to the semantic ones because they're mini-columnar activations. But that model also included a much sparsified sort of dentate gyrus-inspired hippocampal representation that is highly orthogonalized and sort of, in that sense, sort of ideal for full recall rather than familiarity recognition, right? Because the overlap is nil or next to nil.
Yeah.
And the whole point of that model was that the hippocampus can index memories, meaning you get through the sparsification process from a dense representation to a very sparse set of hippocampal neurons that are then going to be active and encode this thing. But then you close the loop by having plasticity in the feedback path. And so very practically, you could just learn that with associative.
Yes, you could.
With associative connections. And in fact, the mechanisms that we now know about in terms of plasticity and let's say this fast dendritic associative plasticity would be perfectly suited to that. Because inside the
But I don't think they're sufficient. There's a capacity problem there.
Right. Okay, well, let's talk about the capacity problem once I sort of make this a bit more biophysical, right? So I'm going to turn these units now to parameter cells.
That's what they are.
Right. And I'm going to argue that locally, there's a high set of recurrent connectivity. So let's say 25% of the neurons actually have some connection here, right? So that if I were to, draw out, sort of dendrites here, the Numenta way of thinking about this, there's a couple of contacts that come from other neurons, right? These might not be sufficient to fire the neuron, but they might be sufficient to do something like what Aaron Milstein described, which are these dendritic plateau potentials, where when these units activate, you just raise the membrane voltage a little bit. And the cool thing is if you now have the tiniest amount of back projections, so of specific cells, right, which actually feed back onto the same dendrite, then recent experimental evidence shows that you are capable of one-shot learning this cell being able to drive this neuron now. Because you get a coherent activation of this together with the sparse representation. Entorhinal cortex is a loop. The same area that projects into hippocampus to generate this sparse thing, right, through the dentate
Because,
gyrus.
you know, this, in the
Also
cortex,
projects
in
back.
the cortex, these are the same cells, remember. I'm not, it doesn't disagree with what you're saying, but
Right.
in this diagram, they're the same cells. There isn't the one place and another place. We're talking about those many columns are the same as those many columns at this one point in time, right? So just remember.
Right. For me, these are different brain areas.
Yeah.
And for me, this is the supragranular layer of entorhinal cortex, and this is the infragranular layer from entorhinal cortex, and this thing is the hippocampal loop.
Okay.
Right? And so this is CA3, CA1, super
Okay,
sparse
but
representation.
I want to make it work in the cortex where they're the same area, the same cells.
Right.
I don't think that's a problem. I just want to point out that.
I only wanted to point out there are biophysical mechanisms and well-identified and by now studied forms of plasticity that can do exactly that, that can bind the super sparse index back to the semantically useful representation.
So I can go for that. There's a problem. There's another trickiness of this whole thing, and I'm going to focus on sequence memory like melodies again. If I'm listening to a melody and I'm tracking along, I'm in this very sparse representations here, and I make a prediction of, I hear in my head the next element that's going to be, next note that's going to be played. I'm not confused by it. I know that it's a prediction and not the real thing. And so I actually really don't want to activate those cells again. At least I don't want to activate on the same cycle, or there has to be some distinguishing point here. And I've asked myself, well, how is that? I mean, we've modeled this as silent predictions. Like I have a silent prediction, which is the depolarization of the cells, and I'm not aware of those. I just notice them when they're wrong.
Don't activate the units.
Don't activate anything. It's like I make a zillion predictions about the world, and I only notice any of them if there's an error. But in this particular case, I can actually anticipate hearing the next melody, the next song note, but I'm not actually hearing it. And so there has to be some distinguishing characteristic between the cells that are active when I'm predicting it and the cells that are active when I actually get it. There seems to be two possibilities. One is that there's actually separate populations of cells that are involved here. Another one is that they are different cycles of some phase of some cycle, something like that. I'm not disagreeing with what you said for me. I'm just throwing on another problem that has to be dealt with here.
Right.
So when we go back and forth between these two projections, very often we're going back to predict the next input, and it's not the same thing as when it happened. So I don't know the answer to that question either. Anyway, it's possible that your solution would work. Probably does. You probably tested it, but I'm still puzzled by the complexity of the overall problem.
Yeah, it's not as simple as I drew it, of course.
Yeah.
I wouldn't suggest
and
it.
Now you're saying, okay, of course I have to take this population, and it has to be a population. It can't be individual cells. It has to be a population code that's going to now, basically you're saying all I have to do is learn that projection from here back to here. I have to learn it. But I only have to learn it on one cell is what you're saying.
Right, or very few enough that the recurrent connectivity will do the rest.
But if I don't do it on one cell, if I take these 4 cells and put them on 4 cells here, then I can't recognize the population code anymore. Then there's a whole bunch of errors that I believe will occur because I'm not requiring somebody to recognize these 4 cells at once because I'll have what we call mix and match errors.
Right.
So it seems to me that this population code has to be recognized on a dendritic segment someplace, or multiple dendrites, but each one has to represent a subsistent portion of this. So now we're basically, if I have 10 cells in my mini column here, I've just increased my capacity by a factor of 10, but I still have to learn each one of these patterns over here. I have to learn that this particular note in the melody goes back to this, and the next particular note in the melody goes back to this. I suppose I could learn that. I have all the information as I'm going along. But it just seems to me that's a hell of a lot of learning.
Right. It would be nice to get around it, yes.
Yeah, and then I have to somehow preferentially pick one of these cells to learn this pattern, but not all of them, because if I try to learn all of them back to square one, I have a problem there.
Well, you can do you probably still want to do the sequential activation and things, right? or using, the SDR math, as you call it, right? These highly
The peer, from
Right.
this to this. to
right.
this,
So you
yes,
want the fast place cell sequences, right? You want them to reside in CA8, CA3, right? The sequences that integrate the full path. Right.
I just hope we should keep going back to cortex because I'm not as comfortable with where these cells are. And
Okay,
right.
I'm sorry that they're kind of in the wrong brain area, but for me,
We can just talk about it as a generic problem. Just these parse code. And
okay, so you still want to probably do fast sequences using the more sparse representations,
Yes.
because you want very distinct transitions,
Yeah.
right? And the bigger
the
semantics
sparser
of
you
this.
get here, as long as you have enough active cells, the sparser you get here, the higher capacity. and
Right.
the quicker you can learn.
Yeah, so the
If you-
semantics is in the bigger thing, in like the name of the sequence, right? To use the language of your first book. And so in that sense, it might be useful to not think of this as a super fast loop, but like a slower loop, right? That binds back together this sequence of activations on the right side with more semantic, slower representations on the left side.
This is not slower. This is the in the melody example. This is the note, the current input note out of context. It changes this changes just as often as this. It's not the name of the tune. That's someplace else. That's the tempo puller. We're talking about here. This is one layer of cells we're talking about here in the sequence memory, where you have mini columns that represent at one moment they represent the if all the cells, the mini column itself represents the generic input. It's specific, this or this, but this representation represents that in a particular context.
Right.
But it's not the name. This is not slower. That's not. I'm sure maybe we're confusing that. In our model, there's a separate tempo pooling layer which is trying to be stable over all of these.
To get the name. Right.
Yeah, that one has a learning capacity problem. That's a real learning. This we can learn. You can learn one layer of cells in one quarter column. You can learn 1 million sequences here, or 100,000 elements. But you can't do that up in the pooling layer. That's limited. And so you can learn more sentences and more melodies, and you can learn names of them. Anyway, so maybe we're talking about different things. I'm just trying to get back to this changes just as often as this in the temporal memory model.
In my mind, there's one more thing to keep in mind, because if we want to think about mechanisms that can sort of activate the whole column, because we want to get back there for whatever reason, right? And I'm just thinking, what kind of mechanisms does the brain have for that? And one of the most useful ones is the actual input state, the layer 4 cells, because like experimenters have shown again and again, that the neurons that are recurrently connected, so cells like inside the mini column, right, are likely to also share the same layer 4 cell input. So in that sense, you can recruit, right, the column by activating the layer 4 input cells.
So it's funny because I would argue this might be all layer 4 here. So I'm getting a little confused there.
Right.
I'm going to pick up on something you said. There's another possible mechanism here, is that the bipolar cells that basically define mini column, the
double bouquet cells,
double bouquet cells are all forms of bipolar cells. They also have a learned receptive field which matches the cells here, the feed forward. So if I looked at the bipolar cells here, it's going to have the same feed forward response property as these cells, but it won't have the specific representation that these cells have. So if I want, just as a mechanistic observation, if I wanted to invoke the mini column, I could do it just by invoking the double
bouquet cell,
cell.
or bipolar cell, if you want to call it.
So that's another possibility. And as people have been around for a while, of course, these mini columns run throughout the entire cortical column, and so it always felt that there's some deep representational schema that's happening across the layers that's relying on the mini columns for various transformations, and we've never been able to figure that out. It just seems like a critical part of the whole solution. when we talk about grid cells and orientation cells, and it's something we've never figured out. So it feels like there's these two sort of mechanisms. There's this mini column mechanism, which is bringing information across the layers. That it's this semantic meaning. Somehow the semantic meaning is being shared across all the layers in the cortical column, right? And that's one mechanism. And then anytime the cells project someplace, you're in this domain.
Much more.
Marcus, did you have a particular point you wanted to make today, or just sort of bring this sore topic up again?
The point. So I mean, I've laid out a lot of the groundwork of. We're talking about there are these two types of SDRs. These ones you can't really cool them or union them.
Yes. But why did you bring this up today? What was the?
Because I'm trying to understand where all this math we have that talks about unioning and pooling and random patterns fits into deep networks.
Okay.
And it feels like we have to somehow make this leap before they'll really apply.
You're saying the deep learning networks are in this domain.
Yeah.
Mm-hmm. Would everyone agree with that?
It's like, and that is an open question, but like to.
No, I definitely agree with that.
Okay,
Yeah.
so it's like you could think of this sort of as stacking spatial poolers, where we're putting k-winners on each of these. The k-winners here. It's like an advanced, more machine learning
Yes.
version of spatial poolers.
Let me ask you this question. So I see that. I can see why this is sort of the domain of deep learning networks. But now we require this domain here to learn sequences, but deep learning networks don't. They use the what do you call it?
LSTM.
LSTM, thank you. How does LSTM fit into this? Does it? I mean, how do they somehow achieve the same result as this, but they don't do this with a sparse representation like this? Is there some simple summary of that makes sense? Or is it too hard to explain? I mean,
They can't do the unions that we can. So they
do they have a representation that says, that's this input in this context?
yeah.
Because there's memory representation.
How does it remind me how that works? Is it simple to say?
So you have the recurrent connection, so
Yeah.
that's taking charge of keeping your state in the representation that it somehow.
But that's a very, very specific states, right? So are there separate sets of cells for that? I forget.
I think it'd be just some dense vector acts as a context for the next dense vector. Just like we have sparse vectors act as context for the next.
It's not as memory efficient as the SDRs, right?
But they can still solve the basic high order temporal memory,
Yeah.
high order sequence problems, but they can't do unions. Right? So if you have ambiguity and you start in the middle of a sequence, they kind of fall apart. As an example. That's one example. So we laid this out in our sequence memory
I forget.
in our neural computation paper.
I'm sorry. I got all that stuff and understood it one time.
But part of Jeremy's thing, what he did was try to get a deep learning version of the temporal memory.
That's
So
right.
he tried to, but he couldn't. He ran into this exact same issue. So he kind of ditched the mini column structure, but still kept some of the other stuff.
So Marcus, is your point saying, I'm going to try to get to a high level thing that I can keep in my head, that the world of deep learning is really focused over here right now, and there has to be sometime it has to go over here to do the things that the brain does. Or is that would be a summary of what you're saying?
I would say that I don't know if that's the answer. I would say that if we did figure out a way to make this leap, suddenly the properties of SDRs that we know and love would be all over the place, like we would care.
I feel
But
confident.
then we lose this quote unquote generalization thing of
It's an
similar
open question.
things. Yeah, similar things. And
It's
that's
not-
exactly what Jeremy was
Yeah.
trying to get at. Yeah.
So again, that requires going back and forth between these two worlds, right? If you can go back to this world, then you can generalize in some sense.
Well, they can't exist entirely in parallel. That's at least the argument that cognitive neuroscientists make about the so-called. I should probably point you towards one of these review papers by Yonil and us, with it puts that in very nice cognitive neuroscience terms that you would understand. Where just making the point that these different memory systems do exist in the brain, and you can impair them differentially, so they're actually independent to a large degree. You can impair familiarity recognitions without impairing contextual memory, and you can impair contextual memory without impairing familiarity sort of global match
This
recognition.
is all in the hippocampal complex, is that right?
No, yes and no. So these are the structures outside the proper hippocampal loop, so perirhinal cortex, doing these more generic, denser representations that enable global match computation. So recognizing whether something is familiar or not, as opposed to hippocampus, which you definitely need if you want to recall contextual memories and do things like, like a full recall of specific episodes. And these systems do not rely on one another. They're actually separable in the sense that you can impair one without impairing the other. And there's plenty of disorders where you lose one, but not the other. So you are no longer you're capable of seeing that something is familiar, but unable to ever recall the specific context in which you saw it, or other cases where people can recall specific things, but are unable to compute something like a global match and say whether it's familiar.
Hearing you talk about that, I wonder if it's really the same problem we're dealing with here.
I think it is, because you say that's exactly what you lose.
Yeah,
It's
but
the
it's
context
like,
that
I
you
don't
gain
ever,
with the sparse
it's not like
representation.
I remember, I'm not sure. The hippocampal complex is solving a whole bunch of problems some problems that the cortex doesn't solve. And there's a whole idea of this memory of my recent events and what I've done is clearly happening in hippocampal complex. It's not clear that it's happening here. I mean, I'll just put it aside. Maybe if you have a good review paper that talks about that, I send me the link.
Yeah.
Okay.
Okay, we should wrap
wrap
up
up,
soon.
yeah.
Anything else? I totally agree with you that jumping to something like that would help a lot of these issues.
I have a question. We don't have to necessarily, continue in this room, but I was just kind of curious, when you mentioned the dentate gyrus and the loop, why is it necessary?
Why is what necessary?
Why is that?
Why is it dentate gyrus?
Yeah, why is it
Why is it
necessary for
necessary?
that? The encoding mechanism you mentioned there seemed to be one of the things that broke the analogy for Jeff to say things go back and forth. I was just wondering what it was specifically that aggregation does.
It's necessary to get to SDR mark, to get very specific memories, to be able to not just learn generalities, but learn specifics.
Okay. And are there any parallel connections that hop over it and go directly?
Yes, of course. That is the whole point. That's why there's parallel systems in the brain for a lot of these things.
Okay. So the fact that it's consolidated in a particular structure is what I guess, Jeff, you're saying breaks the analogy for everything.
I wouldn't say it's breaking. I wanted to point out that what Florian was talking about is not exactly what I was talking about.
Right. I made an anatomic argument that is uncomfortable. I understand that.
I wasn't even uncomfortable. I just wanted to point out there is a difference, and we should need to recognize we're talking about maybe two different things. Maybe they work on the same principles. I don't know.
Well, that's what I was saying. I mean, is there if this thing wasn't consolidated, was somehow distributed, would it be more
I don't know.
tenable?
I don't know. I think it has to work in a consolidated form, and it could also work in a distributed form. I just want to point out that I think it has to work in a consolidated form. That's the only thing I was bringing up to Florian. And so I didn't have anything more to say than that. It wasn't like, oh, it won't work or anything like that. I just wanted to point out that what I'm talking about here, I'm talking about the same cells, the same cells, and he was talking about different cells. Right. So it's the same principle maybe applied. Obviously, you would want one cortical region or one cortical column to be able to communicate with another cortical column, somehow invoke the correct semantics on things or others,
That was actually what I was trying to say, whether that the fact that in the hippocampus it's consolidated into the dentate gyrus, if that functionality was in the I'm going to hypothesize higher connectivity of the neocortex, if that is a distributed function there, that's not easily as isolatable into an anatomical structure like that, but it could still be there.
Right.
Yeah.
Yes.
I don't know. Yeah.
Yes.
Okay. Yeah.
I mean, it's just pointing out that these different representations are useful for different things, right? And we find them in different data structures and in different pieces of like machine learning, and it's good to know why both are useful, right? And obviously building bridges between them is interesting.
Yeah. You
So
know,
it's what I take away from
I was
this.
never a student of the hippocampus and hippocampal complex until fairly recently, and even then I consider myself a student of it. But so I always think about these cortical structures, and so we know this very clear many column structure that exists and so on. And when you look at the hippocampal complex, it's much messier and there's more stuff going on there, and you know it's like an older structure that's a catch-all for everything. It's like, oh, remember everything. And then it's like the cortex is more specific. Like, no, I'm modeling the world. Here's the things I'm modeling. I'm making models of these things. The hippocampus saying, I'm going to model the world, and I'm going to remember what you did, and I'm going to remember what your mother looked like, and I'm going to, whatever it was, what you did yesterday. And I don't know. So I think of the cortex as sort of a slimmed down, trimmed up, mini version of what the hippocampal complex does. I might be right, but I think so. Well, that was a fun topic, Marcus. I'm not sure.
It certainly bridged a lot of different ideas.
Yeah, I was like, what are we talking about this again for? Your point is that maybe we should think about this in terms of people.
That's the two sides of the coin. That's one of the sides of the coin. Yes.
Bridging machine learning and neuroanatomy and cortical theory and representations and math.
Well, I find this whole representational scheme really fascinating. It's like the idea that specific neural things, you know.
Thanks, Matt.
This idea that like every neural knowledge.
All right. Hey, could one of you take the double back? I don't know if anyone heard me, but okay. There we go. Thanks for watching. I know there are audio issues and there's bad audio to this. I've tried 5 different mics so far. I'm not an audio visual professional. I just I've been trying different things. So at this point, I'm going to put it in my budget to professionally mic the conference room. So that's the plan.